Okay. So the next thing is called new functions from old functions. So this, hopefully you know this stuff pretty well already. So have you done graphing transformations like add numbers, take away numbers? So if you have a positive number c, and you have an equation that's f of x plus c, how do you shift your graph f of x? Up c, exactly. And the fact you had to say it was positive, so you knew that it was up and not down, right? What about f of x minus c? Down c. Yep. Okay. Now this one doesn't do what you think it's going to do. When you do f of number plus c, it shifts the graph to the left. I have to actually face the board because I'm dyslexic. Maybe not actually dyslexic, but it goes backwards of what you think. This one's going to shift the graph. Mm-hmm. And you can convince yourself of that by, say, like taking the function x plus 2 squared and actually plotting it and like plugging in numbers. You see it's a parabola moved backwards to the left too. Does that make sense? Okay. So when you're graphing stuff like this, my first step is to figure out what the parent function is. That's what my high school textbook called it. And that is the thing you're shifting. Okay. So in this case, the way you find the thing being shifted is ignore all the adding, subtracting happening to it. You just see the function root x, right? So plot that root x function without the shifts. And what's your fallback method to plot a function if you don't know how? Plug in points, right? Plug in 0, you get. Plug in 1, you get. 2 doesn't come out nicely, neither does 3. What's the next one that comes out nicely? 4. Can you plug in negatives? Nope. Okay, so there's the root function. And then what does minus 2 do to it? Goes down 2. You don't have to draw the parent if you don't want to, okay? I'm just going to do it for, like, being clear in class.
You should have the parent all the way up there.
But that would give you a hint at what it was, and I want to make sure you can construct it without actually, does that make what we give it to you? Does that make sense? Because for these questions, in my experience, most of the problem that students have is they don't know what the parent looks like. They get the whole general shift idea, but they can't figure out what the parent is or what its picture is. Does that make sense? So part of it is like just knowing what they are and how to find them. Also doing that means I've got to make different pictures, which is really complicated. Okay, for this one, what would the parent function be? ln of x. And unless I'm mistaken, most people have forgotten what ln of x looks like, right? Maybe not. If you haven't, I'm really happy. We're going to discuss this more in a later lesson, but this thing is the opposite, or mathematically formal word, inverse of the function y equals e to the x. E is an irrational number like pi that's close to 2.71. Okay, just a little bit of background. If you were to plot just e to the x, when you plug in 0, what do you get? 1. When you plug in 1, what do you get? E to the first, so approximately 2.71-ish, right? So over 1 up 2.71-ish. And that's going to keep growing, right? You're going to get e squared, e cubed, whatever. They're going to be huge numbers. How will you plug in negatives? Like -1, you get e to the negative first. I'm very Lilo and Stitchy. Negative exponents have to be punished. You see that movie Lilo and Stitch where she punishes her dolls in the little jar? Okay, no, it becomes, 1 over e. I did a lot of baby scenes. I watched a lot of baby movies. So if you've got a calculator, what's 1 over e approximately? If you don't mind. Because I can't do that in my head. I'm not that amazing.
1 over 2.7.
Yeah, I mean, so it's small. It's a little bit less than a half, right? Or about a third. That's a good estimation. But it gets little, right? What about plugging in like negative 1,000,000, 1,000? It gets close to 0. Does that make sense? So this is what the e to the x function looks like. It never, ever crosses that. What did you get for it, 1 over e? 2.7. Okay. It was 1 over 2.71, which I think close enough to about 1/3 is good enough for us, okay? That's what e to the x looks like. That's a model for population growth if it has unlimited resources, as in it never hits a carrying capacity then because it's unlimited. Okay, it also is a good model for like money, if you put money in a bank and you have like things appreciating. So, or for banks borrowing money from you and how their money grows when you give them money for your house. Now, ln of x is the opposite of that. And the way you do opposite functions is that the x's and y's flip-flop. So if I asked you to graph the function natural log of x, you take the values in the table and you flip-flop them. So when I plug in 0, you get out, when I plug in 1, you get out 0. When I plug in e, you get out 1. You see that just flip-flops? When I plug in e to the negative 1, you get out negative 1. So you go through 1, 0, e and 1, and then you go over some positive amount that's close to 0 and down negative 1. If you don't know that parental picture, I suggest a flashcard. Okay, you have to know what ln x looks like. It is required. It is Algebra 2 and pre-calculus. It's kind of like a square root function, isn't it? I mean, root functions only are part of, there's only like, they don't cover the entire plane, right? And you see how, so look at also, what is the domain of that ln function? What's the leftmost value it gets to? Or doesn't quite get to?
0.
Uh-huh. It doesn't quite hit it, because the e to the x doesn't quite hit y equals 0. So the ln doesn't quite hit x equals 0. And the range of it is -infinity to infinity, or all real numbers. Okay, so step 1 is what does parent look like? And then step 2 is graph the function itself. So now that you have this parent, how will you shift it? It'll go to the right 2 and down 5. This vertical asymptote will also shift. So I'm going to shift that right 2 and just sketch it in. Okay, so over 1, 2, 1, 2, 3, 4, 5. That function, at least, I mean, it goes through some other points exactly, but this is kind of the important point it goes through exactly. We'll be checking that point and that your asymptote's in the right location, and that you got the general correct shape of the picture. But we will discuss e's and ln's more tomorrow. By then, hopefully, I'll stop coughing, but probably not. Okay. So how about this? What would a number that's outside the function do? Is it going to stretch it vertically, or is it going to shrink it vertically? It's going to stretch it vertically. I know it might compress it this way, which I think is a little bit hard to think about. We'll think it's going to do a vertical stretch. So by C vertically. Sometimes vertical stretches also equal horizontal compression, so I know that's like a little bit tricky, but not always. If you multiply by a number that's 1 over C, where C is bigger than 1, so like by a half or something, that's going to make the graph shrink vertically. So for example, you could think like 2x squared, you could think 1/2 x squared. And you could compare those to x squared. In the first case, it's like taking the x squared picture and stretching it. The second one's taking the x squared picture and squishing it. Pull it versus step on it. Okay. Now, if you put a number inside, this compresses the graph by 1 over c horizontally. It's a horizontal squish. And if you divide by c, it's a horizontal stretch. And I will have pictures of both of those eventually. All right, how about the last two? These are the more important ones. What does a negative outside the picture do? Outside the function? Flips it over the x-axis. Great. It takes what was a positive y, makes it a negative y. It takes what was a negative y, makes it a positive y. Just flip-flops that. So if that does over the x-axis, what does putting negative inside the function do? Over the y-axis. And you see that one a lot less because when you first learn to do transformations, we use functions like x squared, absolute value, and reflection over the y-axis just produces the same picture. Does that make sense? So those are a bit silly. Okay, so will this picture be taller than a regular square root function or more squished than a regular square root function? Taller, exactly. So the way that I think is best to get the specific points is to just graph 2 root x by plotting points, and then once you've got that, shift it around. If I give you a grid, you've got to put the dots in the right places. Does that make sense? No fudgy-wudgy there. I know, dang it. Okay, but it's not that bad. Plug in some numbers. When you plug in 0 into 2 root x, what do you get? Don't tell me now. 0, okay. When you plug in 1, you get 2. And when you plug in 2 icky, 3 icky, 4. 4, you get 4. It took the original y values of root x and multiplied them all by 2. Does that make sense? So the original values of root x were this. You see that? So this y value was 1, it became 2. This y value was 2, it became 4, right? Okay. And then take that stretched out picture and move it left 3, right 3, up 3, down 3. Which one? That way? That's right, isn't it? Okay, yeah, move it right 3. 1, 2, 3. Okay. 1, 2, 3. There you go. Well, that picture is awesome. So what is the domain of this function? What's the first number you can plug in? Mm-hmm. What's the range of the function? What's the lowest y value it hits? 0. Great. Awesome. And I will give you like grids on quizzes and stuff because it makes my life easier for grading them. Some people don't like that I do that, but I just choose to not care. Whatever. They can grade stuff that's crappy if they want to. I refuse. I can't draw straight lines, can you guys? Very rarely. It makes me angry. I spend a lot of time trying to make them straight, and then I fail, and I get frustrated. Okay. So with this one, there's a couple things going on. This negative means we're going to do some reflection over which axis? I think that was over, I guess that one actually could go either way. It would be the same thing, but technically it's over the x-axis. But you actually could phrase that so it was the y-axis in this question. You would not be wrong if you did it the wrong way because you're going to get the same picture. What's the plus 1 going to do? This really is a positive 1, right? You could think about this as negative 1 over x plus 1, right? Same thing. It's going to take that flipped thing and it's going to move it up 1. So first of all, let's figure out what is the parent function. What is this thing you have to graph? And the parent function is 1 over x. Does that make sense? Ignore the 1 being added, the negative. Just graph 1 over x. That's called the reciprocal function, because it's, 1 divided by a number. It's the reciprocal of a number, right? What are some numbers that work out nice? 1. When you plug in 1, you get out? Okay, when you plug in -1, you get out? -1. And everything else is stupid, right? What do you get when you plug in a half? What's 1 divided by a half? 2. 1 divided by a third is going to be 3, right? So what's going to happen as you get closer and closer to 0? You're going to go to infinity. Does that make sense? What's going to happen when you plug in 2, 3, 4, 5, 6, etc.? What's going to get closer to 0. I'm not going to grade your accuracy on fractions, okay? Make it obvious it doesn't go back up, but, I'm not going to grade your accuracy on fractions. How about the negatives? 1 divided by -1/2 will give you -2, right? So this one's going to look like... So that's an example of a function that is called discontinuous because it's in 2 pieces. There's a break in it. And both parts of it are part of the function. So you can't only graph half. You've missed half of the picture. Okay, so first, there are ways to get around this, but in general, it is best to do reflections first. It's kind of like PEMDAS. You multiply before you add, right? The reflection thing is like a multiplication that you do that before you start doing the adding stuff. You can get around that if you do your reflections carefully, but I think it's best to just reflect and then shift. So you see how if you reflect this over the x or y axis, you get the same result? So we're just going to reflect over the x, but over the y is the same thing for this picture. I'm going to color code that and draw it in a different color. So that flips this down here, flips that up there. And what's the last thing you do to it? Shift it up 1. If your function has asymptotes, you've got to draw those in again. So the y-axis is an asymptote, and so is the x-axis, right? The y-axis is already dark, don't worry about that, but this x-axis asymptote also moves up 1, right? So let's just draw it in as a dot. Usually they're drawn in as dotted lines. And make it pretty obvious your picture doesn't cross those things. I'll try to remember. I've got like a container of like 70 fun colored gel pens, and I'll bring them in for exams, and you can draw your final answer on a colored gel pen if you want to. I'm sure that'll make your day. No? No one's buying? Okay, whatever. All right. Have you guys ever heard of this technique? Complete the square. I did not learn it well when I was in high school or in my pre-calculus class, so maybe you've seen it, maybe you haven't. It is one of those things that you're supposed to review on Alex if you have not done so yet. So this would be super, super nice if it was like x plus something squared and we could shift it around, right? Does that make sense? So a way to make that happen is to plot points, or to complete the square. And this will come up again, so it's good to review it. So the name completing the square hints a little bit at what you're supposed to do. You're supposed to add a number in to somehow make this something squared. So we're going to add a number in here so that we can factor this into x plus something or x minus something squared. And the number to add in is 9. And I'll tell you why in a, well, except that's what it is for now. We'll discuss how you figure the number out in just a moment. So if I add in 9, how does x squared plus 6x plus 9 factor? just this part, x plus 3 squared, right? When you added in 9, it became something squared. Okay, so now how did I figure out to do 9? What was the pattern? How is that 9 related to that 6? Mm-hmm. Yep, it's half of this.
That should be a negative 6. Should be negative.
Oh, I'm so sorry. Thank you. Let's see if I can actually erase it. That should have been negative 6. Whoopsies. Does that change the result of the 9, though? Nope. And this should be then minus 3. So everyone okay with that part of it? So that's how you figure out what to add. You take half of the coefficient of the linear term and square it. And you can feel very, very like, okay, you can't just add 9 to an equation and claim it's the same thing. That's totally wrong. Do you feel like that's, yes? So you clever. You added 9. How do you compensate and make sure you've actually added nothing? You could either minus 9, or you could add 9 to the other side, which is the same as taking away 9. Does that make sense? Okay, and so now you've effectively added nothing, right? The first 9 is built into this thing, and then what's 4 plus negative 9? Negative 5. How could you check that you were correct? Because I claimed that this is the same as this, right? Same means equal. Couldn't you do x minus 3 times x minus 3 and then take away 5 and you should get back that thing you had originally? And that'd be x squared minus 3x plus 9 minus 5. Bam. Same thing. With the clever trick where you add and subtract something, will come up again in this class, okay? So, and it's really useful for graphing parabolas because now, can you graph the parent function x squared? Yeah, good. Okay, what's that go through? 0, 0, 1, 1, negative 1, 1, and 2, 4. And then how do you shift it? Left or right? Right 3 and down 5. Great. There you go. There are other ways to plot that function, I mean, including like plotting points, and you could plug numbers into the original function. It's just hard with parabolas to know where to start and where to stop. So that you plug in negative numbers, you'd get like humongous results out. And you'd be like, oh my gosh, what should I do? Start plugging in some positive numbers. But this trick is a really good one to know because it makes graphing parabolas of a specific type especially pretty much easier. And the whole completing the square thing again, like will come up for other stuff as well. So it's just good to know. Okay, so the graphs that make the most sense when you talk about like compressions and stuff are the sines and cosine graphs. So let's graph 1 minus cosine x. So we already discussed what cosine x looks like. So I'll call this pi halves, pi, 3 pi halves, 2 pi. So in this one, we're going to call that 1. So where did cosine start? On the y-axis, that is. 1. Crossed at pi halves was at negative 1 by pi, 0 at 3 pi, 1 again. And then do the backwards part as well. Which kind of is a copy-paste. And if I give you a sine or cosine function in the graph, I'm probably going to give you a specific interval. And usually it'll be negative 2 pi to 2 pi because I want to see if you can do like the negative half and the positive half as well. Okay, so this is the same thing as negative cosine x plus 1. What does the negative do to it first? Over the x or over the y?
X.
Over the x, okay. Flip it over the x. It's like connect the dots, you know, it's like a fun game you played when you were a kid, right? No one's having fun. Okay, I get it. Okay. And then what's the final thing you do to that picture? Move it up one. Man, my art looks messed up. So sorry. And it would keep going. What is the domain of that function? Say that again?
0 and 2.
Well, we only graphed a portion of it, but the pattern's going to keep going forever and ever. So the part that we graphed was negative 2 pi to 2 pi, but it actually is all real numbers because it does go and continue on both sides. You have the range, though. The range is 0 to 2. That's all the y values that come out. Okay, great. What do I have next? Sine of 2x. Okay. Stuff inside of functions does the opposite of what you think. So instead of making this stretched out, it's going to make it compressed. And what you can think about is that if x is time, 2x means time goes twice as fast. So you oscillate more quickly. So how long did it take a sine function to go through one oscillation usually? The one that we drew was how long? 2 pi. So we're going to figure out when does 2x equal 2 pi. When that happens is when one cycle is over. So this is when x equals pi. So that's right there. We're calling that pi. So instead of the cycle occurring in 2 pi, it's occurring in pi. So what was sine's general shape? Where did it start? 0. And then it goes up first, right? And so instead of being at pi halves, it's actually going to be at pi quarters now. And then by pi halves, it's at 0. 3 pi quarters, we're at -1, and pi, we're at 0. Okay, we'll graph one more. I'm going to point out another cool pattern. 2 pi. So you go up, down, down, up. How many cycles of sine, like how many full oscillations of the sine function occur in 2 pi? 2. This number is a 2. That is not a coincidence. If I gave you, for example, sine of 7x, sine would oscillate 7 times between 0 and 2 pi. Okay? So that number is how many cycles in 2 pi. Okay? That is always true. So if you see sine of 3x, you should go through 3 full cycles in 2 pi. That's always true. Can you also graph the negative side? Let's just do that, okay? Ish. There you go. I will specify. Does that make sense? But I think that since your homework doesn't specify, do -2 pi to 2 pi. Because I think that there is one question in your textbook from today where you're asked to graph like a sine or cosine function. Do -2 pi to 2 pi, and I'll tell the grader to do that. Yep. And on quizzes and stuff, I'll specify. Okay, what is the domain of this function? All real numbers, yep. What is the range? -1 to 1, great. Okay. When's this class out?
12:30.
Okay, thanks. Whew. We'll get through most of it. Okay, f of x plus g of x. So this f plus g, another way to write that is f plus g of x. And that of x doesn't mean multiply by x. It really just means take f of x and add to it g of x. So that's root x, and that's root of 4 minus x squared. So that's what f plus g of x is equal to. You're also asked to find the domains. So x is bigger than or equal to 0, and 4 minus x squared has to be bigger than or equal to 0. Now, this second thing, if you try to solve it like in an equation, you're going to be wrong. It is probably easier at this point in time, so I'm only going to give you simple ones, is to think about it like we thought about that sign picture. Think about a graph. What does 4 minus x squared look like, roughly speaking? It's a parabola, right? It's reflected, and then it's moved up 4. And where does it cross the x-axis? -2 and 2. So it looks like this, right? So in that picture, which x values are positive? Between what x values is the picture positive? -2 to 2. The point is, if you get too big, the x squared overpowers the 4, and that becomes a negative expression, right? Does that make sense? Okay. So if you have to be both bigger than 0 and between -2 and 2, you're even further restricted to what interval? 0 to 2. Yep. Okay. So if f plus g means add the functions, what do you think fg means in part B? Exactly. So fg of x, that's f of x times g of x, which is root x times root 4 minus x squared. You could write that as 1 root. Write it as 4x minus x cubed. It's going to have the same domain. Still 0 to 2. How about taking a ratio? Is that going to change the domain at all? So I think pretty obviously this means f of x over g of x, which is root x over root 4 minus x squared. Or you could write that as the root of x over 4 minus x squared. That's fine too. The domain on the previous ones was 0 to 2, and it included 2. Can you include 2 on this one? No, because that would make the denominator 0, right? So this one's domain is from 0 to 2, non-inclusive of 2. What if I would have flip-flopped them? What if I would have done g over f? What would I have left out in that case? I would have left out 0. Yep, so I would have a parenthesis around 0 and a square bracket around 2. So the domains are a bit tricky on those things, but I think the actual operations of adding, subtracting, multiplying, dividing, not so bad, right? There's another operation with function called composition. Have you guys seen this notation? F circle g of x. Yep. And so you got to be a bit careful. You have to have the domain of g of x, so meaning the number you plug in has to work in g, and then whatever you get has to work in f. So it's a little bit tricky to find, but we'll discuss some examples of that. But first, just how do you find this? So f of g, that's the same thing as f of g of x. That little circle comes from the word of. That's why it is what it is. Just think back to your Algebra 1 stuff. G of x is equal to what? So that's f of x minus 3. And this means plug x minus 3 into f. So what do you get? Which is the same thing as x squared minus 6x plus 9. Okay, how about g of f? So that's g of f. What's f equal to? And then you plug that x squared into g, and what do you get? X squared minus 3, sorry, right? Yep, okay. And the thing to note is that f of g is not equal to g of f. Does that make sense? When I flip-flop the order, they're not equal. That is, in general, they're not always equal to each other. It's called a non-commutative operation. You cannot change the order matters. In some special cases, they are equal, but we'll talk more about those later. And those don't have funky domains because there's no funky domain issues with lines and parabolas, right? You can put anything into those. There's no division, no square roots happening. The next one has a slight technicality. Okay, so f of g of x. So f of g of x. So that's f of 1 minus root x, or cosine of 1 minus root x. Does everyone agree with the composition? Okay, so first look at the thing inside the parentheses. Are there any restrictions that come from there? Are there any things you can't do? You got to be bigger than 0. So that has to be true to even do the root thing. Is there anything you can't cosine? Cosine's domain is all real numbers, right? So you can cosine anything. So as long as x is bigger than 0, you're good to go. So this guy's domain is 0 to infinity. So you check and see if the stuff inside's okay. Then you assume it's okay and say, okay, well, what about the outside? Doing that next function to that, are there any problems in this case? No. Okay, so there's that one. How about this one, g of f? So it's g of cosine, or 1 minus root cosine. We did one a little bit like that, didn't we? Do you agree? We did root sine. Does that ring a bell? I know it was recently. So you go. So are there any problems here with cosine? Not immediately, right? But in this one there are. What's the problem?
It can't be negative.
So you have to have cosine of x has to be bigger than 0. And so for cosine picture, it's like this. And the parts where cosine is positive are from here to here, here to here. So, like, what are the range of values from that first number to that second number? Negative pi over 2 to pi over 2. How about this next one? That would be 3 pi over 2 to where? This is a distance of pi apart, right? 5 pi halves, exactly. And that's good enough. Just tell me that you get the pattern and give me a couple of the subintervals. It's legitimately pretty tricky. But if I can get you to see, like, okay, I look at the picture and look for where it's positive, that's a really good step. Okay, I bet we can get through 8 and 9. The last couple are really quite easy, so I think we'll be okay if we just skip them. So this one is a composition of 3 functions. So f of g of h. So f of g of h. So that's f of g of h. Lots of parentheses. Anybody a CS person where they like have to be careful about closing parentheses? Yeah. So first you put in h. What is h? Great. And then where does, in which function does root x plus 3 go into? G. So that becomes f of cosine of root x plus 3. And then where does that stuff go in? Into f, into that x. So that becomes 2 over cosine of root x plus 3 plus 1. Does it make sense in this notation that h is the thing you do first? Like if you were to put a number into this, first you would root it, right? Then you would cosine it, right? And then you do 2 over stuff plus 1, right? So the next question we have is what I have is kind of like a puzzle. I've taken 3 functions and I put them together. Tell me what they were. Okay, so here's what I mean. Cosine squared of x plus 9. This is the same thing as cosine of x plus 9 squared. Okay, that's the first thing, is that's what that notation means. So think about it as h is the first thing you do. So what is the first thing you do to x? You add 9. And then what do you do to that x plus 9? Take the cosine of it. And then what do you do to that? So there's the 3 functions that were put together. Okay. And then the last one, quite similar. So what's the first thing you do to x? And probably also add 1. You could actually make this 4 functions if you wanted to by treating the squared and adding 1 separately, but for now we'll just do 3. What do you do once you've squared it and added 1? Take the tangent of it, and then the last thing you do is you 4th power it. I think the last 2 examples will really take like 5 minutes. Can I just do example A of one and an example B of A of the other, just to like get you a little bit of a go, and then you can leave. I'll promise 5 minutes over and I will never do it again. Okay. Okay, so this is doing the same thing with a table. Does that make sense? So what is g of 1 from the table? 2. And then from the table, what is f of 2? So there's f, there's 2. It's -1. It's not any different, right? So it's just finding stuff with the table, that's all. And if you got a number that was like, where you had something to plug in that's not in your table, you'd say, okay, it's not defined. That's also usually a possibility if this was a WebAssign question, which it won't be yet because you're not doing them yet. This one, same thing, but with a picture. Does that make sense? Let's do part B. So that'll be g of -2. So first, plug in -2 into g. So you go back to, and what comes out? 1. So it's g of 1. Then you go to 1, and you say, okay, g of 1 is 4. So same idea, not so bad, right? So we'll call it good enough. There we go.